Hi, I'm Mr. Parker and this is question 7 on the OCR Mechanics 1 paper from January 2011. For more questions on this exam paper, click the link here or check in the video description. A particle P of mass 0.6 kilograms is projected up a line of greatest slope of a plane inclined at 30 degrees to the horizontal. P moves with deceleration 10 meters per second squared and comes to rest before reaching the top of the plane. In part 1 we need to calculate the frictional force acting on P and the coefficient of friction between P and the plane. We'll start by considering the forces on the block. We've got a weight force acting straight down of 0.6 G. We've got a normal contact force perpendicular to the slope, which we'll call R. And we've got a frictional force which opposes motion, so that's down the slope, which we'll call F. Next we'll resolve forces perpendicular to the slope. So coming straight out of the slope we've got a force R, and going into the slope we've got a component of the weight which will be 0.6 G cosine 30. The block's not accelerating perpendicular to the slope, so MA on the right hand side is 0. Rearranging we get R equals 0.6 G cos 30, and if we put that into our calculator we get 5.09 and so on. Because we're going to need this answer later, I'm going to store it in my calculator as A. To do that I press shift and then the store button here, and then I press the red letter here, A. So in future when I need to access that on my calculator, all I need to do is press the alpha button and then A, and I can use that value. Now that I've got the normal contact force, I'm going to resolve parallel to the slope. As the acceleration is down the slope, we'll take that direction to be positive, and we get F plus a component of the weight force which will be 0.6 G sine 30, and that's going to equal mass times acceleration, so 0.6 times 10. For the next line we'll do a bit of simplifying. We'll leave F on the left hand side, we'll simplify 10 times 0.6 to just be 6, and sine 30 is a half, so this term will become minus 0.3 G. Working that out on our calculator we get 3.06. Now that we know F and R, we can use the fact that F lim equals mu R. Rearranging that gives us mu equals F lim over R, so we get mu equals 3.06 divided by 5.09. We stored the value for R in our calculator as the letter A, so we can do 3.06 divided by A, and that gives us 0.601 if we round to 3 significant figures. In part 2 we need to find the magnitude of the contact force exerted on P by the plane and the angle between the contact force and the upward direction of the line of greatest slope. First of all we need to do that when P is in motion. So we've got the same force diagram as we had before over here, and we're interested in the contact force. And that means we're looking for the resultant of the frictional force and the normal contact force. So we can draw a little bit of a sketch up here with the slope. We've got our frictional force coming down the slope. We've got normal contact force coming out of the slope. And if we move these vectors to make them top to tail, one on top of the other, we can make this into a right angled triangle where the contact force is the hypotenuse. So to find the value of the contact force, we can do c squared equals f squared plus r squared, in this case 3.06 squared plus 5.09 squared. Square rooting to find c, we get 5.94 if we round to 3 significant figures. We also need to find the angle it makes with the upward direction of the line of greatest slope. So I'm going to put an angle inside my triangle here called theta. We're actually trying to find the other angle on this straight line in the upwards direction with the slope. Here we're finding the angle in the downwards direction with the slope. But all we need to do then is take that away from 180. So to find theta, we can use SOHCAHTOA here. We've got opposite over adjacent we know, so we can use tan theta. And the opposite is R, which is 5.09, and the adjacent is F, 3.06. So we need to do inverse tan of A over 3.06. That gives us 58.99 and so on. So to find the angle that we want between C and the slope in the upwards direction, we need to do 180, take away that, and that gives us 121 degrees if we round to 3 significant figures. In part B, we need to find the magnitude and direction of the contact force when P is at rest. Now this part is quite sneaky and catches a lot of people out. As the particle has reached its highest point, it now wants to go down the slope. So first of all, we've got no friction down the slope and no acceleration. Now we have a frictional force up the slope here. However, the frictional force here will not be the same value as the frictional force over here. And that's because before we had limiting friction. But if we think about the forces going down the slope here, that's going to just be the weight component here. So that's going to be 0.6 g sine 30. And if we do 0.6 g sine 30, we find that we get 2.94. So what that means is the component of the weight down the slope is 2.94, which is less than the value of limiting friction. And remember, we only needed just enough friction to oppose motion. So because that value here is 2.94, that means the frictional force for this part of the question is just 2.94 newtons. So we'll draw a new diagram now. We've got our slope and our friction going up the slope. We've got our normal contact force here. So our total contact force will go between the start of F and the end of R. Notice this time, but when we put the angle theta in here, it's actually between the upwards direction and the slope. So when we calculate theta in a minute, that will actually be the value we're looking for. So to calculate C, we're going to do a similar calculation to what we did up here. We get C squared equals 2.94 squared plus 5.09 squared. And square rooting that gives us C equals 5.88 newtons. Finally, to find the angle theta, we do a similar calculation to up here. So we get C equals the inverse tan of 5.09 over 2.94. And that gives us 60 degrees. So this time the angle between the upwards direction and the slope and the contact force is 60 degrees.